Hello everyone, welcome back to our subject computer organization and architecture. Okay, so in the previous topic we have seen about fast multiplication, is it not? So using bit pair recoding method and carry save method, carry save addition method, we have seen how to perform the multiplication in short duration. Okay, so in today's topic we are going to see about integer division. Okay, so far we have seen about addition, subtraction and multiplication, and today we are going to concentrate on division. Okay, how division operation is carried out by the logic circuit in the processor. Okay, it's quite interesting, and there are two algorithms to carry out the integer division. Both we are going to see it. One is the restoring division algorithm and the other is non-restoring division algorithm. So these two algorithms are quite easy and also very important topic. So let's focus on that two algorithm in today's session. Okay, so before that here is a manual calculation for division. Okay, so everybody will be knowing it, is it not? So I think it's not required for you to have a recap of this division. Okay, the same thing is carried out in the a binary system. Okay, so generally, so this one is the divisor, and the thing which we need to divide is nothing but the name dividend, and in manual paper and pencil calculations we will be following this type, is it not? So the top one is the quotient and the last one is the remainder. Okay, so here in this example divisor is of 13. Okay, it's a binary representation of 13 is 1101, and what we normally do, first 4-bit number, so we will be taking the 4-bit number. Okay, so here 1001, so this is less than 1101, is it not? So what we will do, we will move to take the 5-bit number. Okay, and we will be doing the repeated subtraction. Okay, so here in binary system we will be having everything in terms of zeros and ones. If a number is divisible, if we subtract the number and if we get the number if we get the remainder as 0 or positive, then we will be putting the quotient as 1. Okay, then we will be bringing down the next dividend, and the operation gets repeated until we reach the number which is less than the divisor, is it not? So this is the manual division we used to do in our day-to-day life. Okay, so let's have a we are going to implement the same using the logic circuit. Okay, so that method we are saying as an restoring division. Okay, so here what we are doing in the longhand division step, the step involved in longhand division, so that's nothing but the normal division. So what we usually do, position the divisor appropriately with respect to the dividend and perform the subtraction. So division is nothing but repeated subtraction, whereas multiplication is nothing but, yeah, you will be knowing it, that's repeated addition, is it not? So when we subtract, if we get the remainder as 0 or positive, it means we have subtracted it rightly. Okay, so it means we will be putting the quotient as 1, and remainder is extended to bring one more bit from the dividend, and the divisor is repositioned and the subtraction is carried on. Okay, so what happens if the remainder is not 0 or positive? For example, okay, let me take for example, I am dividing 28, so sorry for that handwriting, so dividing 28 by 3. Okay, so this is 28. Okay, let me draw it neatly. 28. So what we normally do, So I am doing it for your easy understanding. I am carrying out this division using decimal number system. The same thing is happening, the same logic is applied to the binary system. Okay, for your easy understanding, I am considering this decimal number. So here the divisor is 3, dividend into dividend, this is dividend, this is 28. So first we will be taking one digit number and we will be subtracting it. Okay, so if we subtract with this one digit number of dividend with the divisor, what we will get? So answer is -1. Is it not? So -1 means, so quotient, there is no quotient, so we need to restore this value. Okay, so by looking into 3 and 2, we normally visualize that 2 can't divide by 3 and we will be taking this 2 digit number. But in the computer system, what the logic circuit will do is it will take like this. Okay, so on 1 by 1 digit. Okay, and after it computes and gets the remainder as -1, so what the logic circuit in the computer system will do is it will put back this number 2 again by adding the it will restore it. Okay, by adding the divisor again. So now it will put back the result. Now we will get the answer as 2. We have restored the previous value and you will be bringing down the next dividend and the operation carries. Okay, this is how the system will implement. Okay, this concept is called restoring. Okay, we are restoring the dividend. Okay, so if the remainder is 0 or positive, here now if we do the division, so how many times it is? 9 times, is it not? So 9 times 27 and we will get the remainder as 1. So this is positive, is it not? So if the number is 0 or positive, we will be having the quotient. So here I am representing in decimal number, but in the machine everything turns to be zeros and ones. Okay, so put the quotient as 1 and the remainder is extended by another bit. So another bit in the sense, take the another bit from the dividend and the divisor is reposition, subtraction is carried out. What happens if the remainder is negative like this in this situation? So the quotient is 0 and we need to restore the dividend by adding back the divisor like this. Okay, now we have restored -1 plus 3 is 2. We have restored it, and what we will do then, the divisor is reposition for another subtraction. So we will be bringing the dividend and we will be repeating the operation. Okay, this method, this concept is nothing but restoring division algorithm. Okay, so here unnecessarily we are doing one more step, is it not? So in non-restoring algorithm we will be avoiding this step. So that's the logic behind this division algorithm. Okay, so this is the circuit arrangement for restoring algorithm. Okay, so this is quite similar to what we have seen in the multiplication. Okay, manually we'll I think we have covered the topic multiplication of positive numbers. The same circuitry arrangement is applied here for carrying out the division operation. Okay, so here a register, we will be using it for calculation purpose. This is an accumulator register. Initially everything will be initialized to all zeros, and here in Q register we will be having the dividend. Okay, and here in M register we will be having the divisor, and one more extra bit in the MSB to indicate the sign of sign. Okay, so here, so if we have the divisor of n bit, means we will be having in the register M we will be having n plus 1 bit, and also in accumulator n plus 1 bit. So extra 1 bit we will be using it to carry out the sign indication. Okay, and so here, so in division we are doing, in restoring algorithm we are doing both addition and subtraction. So when we will be doing addition, when we need to restore the dividend, we have put back the 3, no, -1 plus 3. So there we are adding it, is it not, plus 3. So there we need to perform addition. Otherwise if the remainder is of 0 or positive, we will be subtracting it. So we are doing both addition and subtraction operation in restoring algorithm. So for that the appropriate control has to be generated whether we are doing addition or subtraction. Okay, so and normally in division we will be carrying out shift left. Okay, so shift left operation is carried out, and here we have n plus 1 bit adder to perform the division operation. Okay, so this is the quite simple logic circuit arrangement for restoring algorithm method, okay, for division operation. And now we'll look into the algorithm for restoring. Please pay more attention. So it's quite interesting, simple, and if we lose out any point then it will be a little confusing for you. Okay, so I am repeating, please pay more attention to both the algorithm. Okay, so two algorithms are there to carry out the division operation. Okay, one is the restoring method, the other is the non-restoring method. So in restoring method, what the steps we need to follow is we will be storing the values in registers, like in M register we will be having divisor, and in Q register we will be having the dividend, and in register A or accumulator we will be doing the calculations. Okay, so initially we will be shifting the A and Q register 1 bit portion left. Okay, after that we will be subtracting it. Since division is an repeated subtraction, perform the subtraction of accumulator and the this one is nothing but the divisor. Okay, so after subtracting this answer will be again in the A register, and after subtraction we will be looking the sign bit of A register. If the sign bit is 1 means set Q naught to 0. So here when we shift the Q register, the LSB bit will be left as free. So there we will be storing the quotient value. So in Q register at last we will be getting the quotient. Okay, initially in Q register we will be storing the dividend, and each and every step while dividing the dividend number gets reduced. That reduced space we are using it for storing the quotient. Okay, so since we are doing leftmost division, all the bits from the dividend will be moved towards left by making empty space at Q naught each and every time. So that space we are utilizing to store the quotient. Okay, so don't confuse, I will take you to the example that will make you very clear about what the steps we are discussing here in the algorithm. Okay, after performing the subtraction operation, we are going to examine the sign bit. Sign bit will be always in the MSB. MSB is nothing but most significant bit. Okay, if MSB is 1 means we have the answer as in the remainder is in negative. So what we need to do, so the quotient is 0 obviously, and we need to restore that M. Okay, so it means in the previous example I have seen we have seen 28 divided by 3, is it not? So when we divide 2 by 3, so we will be 2 minus 3, we are having minus 1, is it not? Minus 1 means in binary representation we will be getting MSB as 1. So it means negative number. So there is no quotient. So it means quotient is 0, and we need to restore that 2, is it not? So how we will be restoring? By adding this divisor 3 with the minus 1, is it not? Minus 1 plus 3 is 2. We have restored that dividend. So that's this step it is given here. Okay, so add M back to A. So restoring A. After restoring A, what we will be doing? We will be considering, we will be taking one more digit from the dividend and we do the subtraction. Okay, so otherwise if the A register is positive, it means 0 in the MSB means, so sign bit is set to 1. Okay, so repeat when we reach the when we complete all the dividend. Okay, so if the dividend is of 5 bit number means in binary we will have 5 steps. If the dividend is 4 digit means we will be having 4 steps. Okay, 4 cycles are there. Okay, so please pay close attention. Okay, this is the same thing, the algorithm is represented in a flowchart manner. Okay, so initially divisor is in M register, dividend is in Q register, count n. So n is nothing but the number of bits in the dividend. Okay, don't confuse here, this is not a divisor. Okay, n represents number of bits in the dividend, and initially accumulator is set to 0. And at the very first step in the restoring algorithm, we are just shifting A and Q towards left. Okay, so after shifting, we will be immediately subtracting the A register from M. Okay, after subtracting, we are examining the A register. The result will be stored in the A register, and we are going to examine the MSB of A register. If the MSB is negative, okay, negative means if it is less than 0, what we are doing, we are setting the quotient bit to be 0 and restoring the dividend by adding the divisor back to A. Okay, then we will restore the dividend. Otherwise, we will be setting the quotient to be 1. Okay, and one cycle is over, we are decrementing the count, and we are then and there we are going to check whether the count is reaching 0 or not. So if it is not, means the thing gets repeated. We keep on shift left and subtract the divisor, shift left and subtract the divisor, and go for examining the sign bit of the accumulator. The thing gets repeated until the count is reached to 0, and at the end, when the count reaches to 0, that's it, the last step, the division operation is done, and finally we will be getting the answer quotient from the Q register, and the remainder is in A register. Okay, that's an accumulator. It's quite simple. So I will walk you through the example. Okay, so please pay close attention, have notebook and a pen. Okay, so without notebook and pen, don't listen. So just you have to work it out. Okay, the way which it has represented over in this example. So you must work it out, otherwise listening alone will not help you to solve this problem. Okay, so everybody, I am requesting again to take notebook and pen with you. Okay, so just have running notes for that. Okay, the initial configuration. So what you are doing, we are doing this division. Okay, so you are dividing this is 8, number 8 with 3. Okay, so 8 by 3, what's the answer? Quotient is 2 and remainder is 2, is it not? So that's what quotient 1 0 in binary representation, and remainder 1 0, that's equal to 2. Okay, here it is 8 divided by 3. So that's the thing, we are going to see it in restoring division method. Okay, so initial configuration. So here how many bits of dividend? 4 bits, is it not? 4 bits. So here initially the dividend is in Q register, and accumulator, as I told you, accumulator and M, in M we will be having the divisor, that should be of n plus 1 bit. Okay, so since it is 4 bit, we are making the accumulator to be 5 bit, and the initial configuration is 0, and M is nothing but the divisor, we are representing in 5 bit 5 digits. So 3 zeros followed by 1 1, and count is nothing but 4. Why 4? Because the dividend is of 4 digits. Okay, initially the count is 4, and at the very first step of restoring algorithm, what we are doing, just shift left AQ, is it not? So we are doing the left shift. Okay, we are this line we are going to shift left. Shift left means this is moved to left. Okay, so that means this portion is vacant, that's what in this square box it is empty, and we are shift lefting. So shift left means move 1 bit portion towards left. Okay, AQ. So this is nothing but the divisor, don't do anything with that. So this one, shift left, this bit and this bit, and this bit will be removed off. Okay, from the accumulator. then what we are doing after immediately after shifting left AQ, we will be subtracting it. So subtraction is nothing but here A register is nothing but this one currently, and you need to subtract M. So M is nothing but this one, and subtraction is nothing but take 2's complement of M and add. Okay, so 2's complement of take so M is nothing but 0 0 0 1 1. So 2's complement of M is nothing but, let me write it here, 2. It's difficult for me to write. So 2's complement of M is nothing but 1 1 1 0 1. Okay, so this is the 2's complement of this 00011. Okay, you work it out. So take 1's complement and add 1, you will get this answer. Okay, see here, so 1 1 1 0 1, and you need to perform addition. Okay, after taking 2's complement you do addition, so that is equivalent to subtraction of A register from M. So when we do addition, what's happening, 1 plus 1 is 0 and carry 1, so that's what 1 here. Then 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1. Okay, so after subtracting you need to examine the sign bit. Okay, so MSB of this is in A register. Okay, you need to examine the MSB of A register. It is 1, so 1 means what, you need to set the quotient to be 0. Okay, so that's the algorithm previously we have seen, is it not? When it is 1, okay, when the accumulator is in negative, what we need to do, put the Q naught to be 0 and put back the dividend. Okay, restore the dividend. Okay, so here, so you have put the Q naught to be 0 and you need to restore it. Restore means plus plus M. Okay, so 0 0 0 1 1, you perform addition again. Okay, so 0 plus 1 is 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, carry 1, 1 plus 1 is 0, and then the carry we are removing it. Okay, so since it's a 5-bit number, so we are representing it in 5-bit number. So currently so please watch along with me closely. So currently in AQ register, this is the thing. Okay, after putting it back again, we need to, the first cycle is over, is it not? So what the algorithm says, after restoring it you need to decrement the count. Okay, initially it is 4, now it is 3. Okay, so after that what we need to do, the count is 3, so it's not an end, we need to repeat it. So repeat, shift left. Okay, again we are shifting it. So next, where we stop here, then shift. Okay, shift in the sense again left side, so this 0 is moved here, this is the Q naught, from Q1 it is moved, and here shift, this 0 is moved here. Yes, I am right. Okay, this one, this 0 and this 0. Okay, after that again do the subtraction. Okay, so subtraction is nothing but 2's complement of M and do plus operation over here. Okay, so 0 plus 1 is 1, 1 plus 0 1, 0 plus 1 is 1, 0 plus 1 is 1, 0 plus 1 is 1. Okay, so after subtracting you need to examine the sign bit. Again the sign bit is 1, so what we need to do, put Q naught again here 0 and restore M. So restore M means add M again. 1 plus 1 is 10, I should not say as 10. Okay, it's 1 0, so sum is 0, carry is 1, 1 plus 1 plus 1 is 1 1, so sum is 1, carry is 1, 1 plus 1 1 0 answer, so 0 is the sum, carry 1, 1 plus 1 0, carry 1 0, that carry is removed off. Okay, so currently, so in A register these are the values and in Q register these are the values, and we are decrementing the count again. Okay, and after decrementing we need to check whether the count reaches 0 or not. No, the count is 2, then repeat it. So what we need to repeat, shift AQ and subtract. Okay, so we are shifting it. So this is shifted here, this Q0, Q1 is shifted here, this is shifted, and this 0 is shifted here, 1 is shifted, 0 is shifted here, and after shifting perform the subtraction again. So subtraction is 2's complement of divisor and add. Okay, so here again do addition operation. Okay, 0 plus 1 is 1, 0 plus 0 0, 1 plus 1 is 1 0, so sum is 0, carry 1, 1 plus 0 plus 1 is 1 0, so sum is 0, carry 1, 1 plus 0 plus 1 is 1 0, so 0 is the sum, that carry goes off. Okay, so after that we need to check the MSB, is it not? Here now the MSB is 0. So if MSB is 0 means we know the algorithm says you need to put back 1 to Q0 position. Okay, so the Q0 here it is empty, and now here since the MSB of accumulator is 0, we need to put 1 over here. Okay, so then that's it. Okay, decrement the count. Okay, decrement the count and check whether the count reaches 0 or not. No, it is 1. Then repeat again. Okay, so what we need to repeat, shift and subtract. Okay, left shift and subtract. Are we doing the left shift? Yes, so here we missed out this one. Okay, so Q 4 zeros. Let me check. Okay, that's it. Then Q0 is set to 1, reduce the count and shift AQ. Here in Q0 this is 0, 0, 0. So here it is 1. Okay, so this step is missed out here. Okay, then this one we are shifting it. Okay, if we shift, what will happen, this one will be moved over here. Okay, here 1 will be here, there will be empty space like this, then this 0 will be here, this 0, this one, and this one will be moved here, this 0. Okay, this 0. After shifting you need to subtract. Okay, subtract is nothing but 2's complement of divisor and do addition operation. Okay, so in addition operation 0 plus 1 is 1, 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 1 all ones. Okay, and I'll write here the status of this Q also. So currently in Q register we have 0 0 1, and this is a empty value, and this empty value will be filled based on the MSB of accumulator. Now accumulator is of sign bit 1. Okay, 1 means we need to put the Q0 as 0. Okay, so this is 0. Okay, so after putting Q0 to be 0, and we need to restore it, is it not? If the sign, whenever the sign bit is 1, we need to whenever the sign bit is 1, it means the negative remainder, so we need to restore the remainder by putting back the divisor. Okay, so putting back in the sense add the divisor to this accumulator, and after adding, what we will get, 1 plus 1 is 0, carry 1, 3 1 is nothing but 1 1, here 1, and carry 1, 1 plus 1 0 0, carry 1, 1 plus 1 0, carry 1, 1 plus 1 0, carry 1, that is moved off, and decrement the count. Okay, after decrementing the count, you need to check whether the count reaches 0 or not. Yes, now at the final state the count reaches 0, and that's it, the algorithm stops, and whatever the value present in the A register is said to be the remainder. So this is the remainder, and whatever present in the Q register is said to be the quotient. Okay, so here the quotient is 1 0, 0 0 1 0 is nothing but 1 0, and here remainder is 1 0. So that's the answer. We got it from the manual calculation also. Okay, this is how the restoring algorithm works. Okay, I hope you understood this example. So you please copy down these steps. It's a very important topic. If you have any doubt, please stop me and raise the question immediately to clear the things quickly, because we are handling the numbers in binary systems. So all the numbers are in terms of zeros and ones. So if you have any question, so raise it immediately. Okay, that's it about restoring algorithm for division operation. Now we are moving for one more algorithm called as non-restoring algorithm. Okay, so here the concept is what in restoring algorithm we have an extra step, is it not? In restoring algorithm, if the remainder is negative, we need to have one more extra step by restoring the divisor. Okay, we need to add the divisor again to get back the dividend, is it not? That is one extra step that we could avoid by using the non-restoring algorithm concept. Okay, how it gets resolved means, so in each and every cycle in non-restoring algorithm, what we did, we have subtracted and added. Here restore is nothing but adding. Okay, at one cycle itself, if the sign bit of the accumulator is 1 means we did two operations, addition and subtraction. So only when we get the sign bit of accumulator is 0, we did the subtraction, no addition is carried out. So that addition can be, that addition is nothing but restore operation, that could be avoided. Okay, and in non-restoring algorithm, so each and every cycle will have either addition or subtraction. Okay, so we could avoid the extra one more step of restoring the dividend by adding the divisor. Okay, it's the algorithm is of two steps. Okay, it's quite simple. Okay, so again for the n times, if the dividend is of n bit. Okay, so initially you will be seeing if the sign of a register is 0, so we will be shifting aq left. Okay, so left shift aq and subtract. Okay, otherwise in the sense, if a is of 1, okay, if the accumulator msb is of 1 means we will be shifting aq and do the addition operation. Okay, so here the subtraction, here the addition, that's it. And each and every cycle it will be either addition or subtraction, we won't do both as like in the restoring algorithm. Okay, so after that, if the sign is after doing this operation, if the sign bit of a is 0 means set q0 to 1. Okay, otherwise q0 to 0. Okay, so repeat it for n times the step 1, and at last in the last step, if we get the remainder as negative, so negative in the sense, if the sign bit of msb is if the sign bit of a register is 1 means we are going to put back at last step. What final step, we will be putting back the dividend by adding the divisor. Okay, so only one time. So in the remaining n times, we won't do we won't put it back. Instead, either we will be subtracting or adding it. Okay, so here is the algorithm flowchart representation for non-restoring algorithm. The same thing as like restoring accumulator, you are clearing it. In m register you are having divisor, and in q register we are having the dividend, and count is equal to number of bits in the dividend. Okay, so here n is nothing but the number of bits in the dividend. Okay, so don't confuse it. Okay, excuse me. Then what you are doing initially, so we will be shifting aq, and you will be checking the sign bit, is it not? So when the sign bit is of whatever it may be, positive or negative, we must shift it, and if the sign bit is positive means we will be subtracting it. If it is negative means we will be adding it. Okay, so a is equal to a plus m, so that's nothing but we'll be doing addition operation when the sign bit is when accumulator is less than 1. So when the sign bit is 1, we will be adding. When the sign bit is positive, we will be subtracting it. Then after this addition or subtraction is over, again we will be checking it whether the sign bit is 1 or 0. So based on that we will be setting the q naught to be 1 or q naught to be 0. If the answer is set to be positive, means we will be setting the q naught to be 1, otherwise negative. If MSB of A is 1, means we will be setting the q naught to be 0 and decrement the count, repeat it until the count reaches 0. And at last, if the accumulator is positive, means that will be the remainder. If it is negative, means we need to restore that remainder by put back the divisor m, okay, to get the remainder. Only at the last step we will be restoring it, and in the intermediate step we won't do any restoration. Either based on the sign bit we will be either subtracting the divisor or adding the divisor, okay. It's quite simple. So I'll take you to the example like to this similar problem. So you please give more attention, take paper and pen, again I am repeating, and work out the problem, okay. So initial configuration for non-restoring division, okay. A accumulator, q is in accumulator, we are making all to be clear 5-digit number, because the dividend is 4-digit, the divisor and the accumulator should be of n plus 1, okay. That's what 5 bit, okay. And count is nothing but 4. Why 4? The number of digits in the dividend is 4, okay. And don't consider these things, we will come back later. And here, so very first step is shift and check the sign bit, okay. Here what we are doing, so this is the initial configuration, okay. So here the sign bit is of 0 in the accumulator, so in the accumulator only we will be checking the sign bit MSB, so 0. So it means shift and subtract, okay. So we are shifting it. So in at the very first step itself, okay, excuse me, let me convert this into pencil, okay. Shift, okay, shift left, again shift left, okay, shifting here all zeros, okay, shift. After that subtract. So I think, oh sorry, it's restoring algorithm, oops, okay. So shift, okay, left shift, here this one is placed here, and this 0 and this 0 and this 0 is removed, okay. After shifting, do the subtraction of divisor. So minus 3 here, minus 3 is nothing but take 2's complement of minus 3 and add it. So this is divisor, and 2's complement of this divisor is this one, okay, and you add it. So subtraction is nothing but 2's complement of that number and addition, okay. Now here you are performing addition, though the thing says here is subtract is right. So here take the 2's complement and add, that's equivalent to subtraction, okay. So 1 plus 1 is 1 0, so carry is 1, sum is 0, then 1, carry 1, then 0 plus 1 is 1, 0 plus 1 is 0 plus 1 is 1, okay. Now you are checking the accumulator, okay. So here it is MSB of accumulator is 1. So 1 means what we need to do in the flow chart, we need to, if it is negative means quotient is 0, is it not, okay. So q naught is 0, so q naught is 0. And now in the non-restoring algorithm we are not restoring the dividend by adding the divisor, instead we are shifting it, okay. Again you are doing the shifting operation, okay. So shift here instead of restoring it, okay. Shift left shift, and this 0 is placed here, this one and this one, okay. Yes, so after shifting it we will be checking the here, go back here, shifting and the sign bit, okay. So accumulator value is of negative, is it not? So right now the accumulator is of 1, okay, so 1 is nothing but negative, so we will be adding it, okay, add m, okay, so m is nothing but 3, okay, 0 0 3. Now you are performing addition, okay, so 0 plus 1 1 1 1 1 1, okay. Now checking the sign bit, again sign bit is 1, so make the q naught to be 0 and shift left, okay, so repeat this operation, okay. So each and every time, so you need to decrement the count, okay, so till the count reaches 0, okay. It's quite simple when compared to restoring algorithm, there we need extra one step. So here either subtraction or addition based on the sign bit, okay. And again the sign bit is of 1, okay. So here we again we are repeating, take the algorithm back, okay. So if it is of negative, okay, if the accumulator sign bit MSB is of negative 1 means we are adding the divisor, okay, so that's what we are adding it here, okay. Here I think we are in this step, okay, third cycle, so we are adding the divisor, okay. When we add 0 plus 1 1, 1 plus 1 1 0 0, carry 1, then yeah, 1 0, here 1 1 plus 1 is 1 0 0, sum carry 1, same thing 0, here 1 and 1, that carry goes off, okay. Now we are checking over here the accumulator, okay. So since it is 0, so now we will be setting the quotient to be 1, okay. If the accumulator after performing addition or subtraction, each and every time you need to check the accumulator's MSB. If MSB is 0 after addition or subtraction, so you will be putting 1 here, okay. Why 1? So since we have the accumulator as positive means its MSB is 0. So if its MSB is 0 means quotient is 1, set the q naught to be 1 and again shift and check for the sign bit of accumulator, okay. So here you will be again shifting it, okay, left shift, this 0 here, this one is here and everything is this one, okay. So here the accumulator is positive, it means what, see here accumulator is here positive, so positive means you will be subtracting it, okay. So that's what at the last step you are performing subtraction operation, okay. So if whenever the accumulator bit is of 0, do the subtraction, whenever the accumulator bit is of 1, do the addition, okay. So here 0, so you are performing subtraction is nothing but 2's complement of m. 2's complement of m is 11101, okay. Then you perform addition over here, since this number is 2's complement and you perform addition 1 1 1 1 1, okay. Then what's it, now after a subtraction and addition at each and every cycle, you need to check MSB of accumulator. So here it is 1, okay. So 1 means you have to put the q naught value to be 0, okay, and we reach the last step. So each and every time you need to decrement the count and here the count is 0, okay. So next we should not shift, okay, instead you need to check the accumulator value at the last step, is it not? So since we have reached the count 0, yes, now you need to check the accumulator is either positive or negative. If it is positive means that is the remainder, if it is negative means you need to restore it, okay. So since it is a negative number, so since I don't have the space, I am repeating over here, okay. So this is the accumulator 5 ones and I need to restore this negative number to be positive, is it not? So how you will be restoring? So you put back this divisor, okay. So you add this divisor, so 1 plus 1 0, carry 1, then 3 ones is nothing but 1 1, so 1 here, carry 1, 1 plus 1 0, carry 1, 1 plus 1 is 1 0, sum is 0, carry 1, 1 plus 1 is sum 0, carry 1, that you are omitting it, okay. And this is the remainder, okay. So remainder at last stage, whatever the value in the accumulator is said to be the remainder, and whatever the value in the last cycle in Q register, this is the quotient. Okay, that's it. Suppose if we get the for some other example, if we get at the last cycle, if we get the accumulator value to be 0, means that's it. So this will be the remainder and this will be the quotient. Since in this example, for this given example, we got at the last step the accumulator value to be negative. Why I am saying accumulator value to be negative? Because I am looking this MSB of accumulator, it is 1. So 1 means a negative number, and at the last stage you need to restore it by adding the divisor with the accumulator value, and whatever we get, that will be the remainder of this division algorithm, given input division, and whatever the value in the quotient, that will in the Q register is said to be the quotient. Okay, so that's it about the non-restoring algorithm, division algorithm. Quite simple. So here we have avoided restoring the dividend by putting back the divisor again. Okay, and each and every cycle, if you note, so will be either shifting and subtraction or shifting and addition. Only these two things are happening, whereas in non-restoring algorithm, if in each and every cycle, if we get the remainder to be negative, means we need to restore. Each and every time we need to restore. That step, extra step, we have avoided in non-restoring division algorithm. So that's it. In both way we will be getting the same answer. Okay. So now moving on for of signed operands. Signed operands in the sense, if the given input is of either positive or negative. Okay, so for this the division operation of signed operands. So whereas in multiplication we have Booth's algorithm to carry out the signed multiplication. In division there is no simple algorithm for performing division of signed operands. Okay, so the solution is, so just transform the operands negative numbers to positive and do either one of this algorithm, restoring or non-restoring algorithm. Do the calculation and get the remainder and the quotient, and finally you change the result to the correct value. Okay, so that's the only thing available for handling the division of signed operands. Signed means, you please remember, both positive and negative. So in division algorithm there is no straight direct algorithm for performing signed operands. So the solution is transform that signed value into positive, do the division operation either one of this algorithm, restoring or non-restoring, and finally change the sign. That's it. Okay, that's the solution for handling the division of signed operands. Okay, so that's it about today's topic, and it's quite lengthy, I hope, because there involves the example calculation, computations are involved. You please make a clear understanding of that algorithm, write it. I am repeating, you have to work it out with paper and pencil, otherwise it's quite difficult to, even though the problem is simple, so it will be difficult just if you keep on listening and going means. So okay, so please work it out. So here today we have seen division algorithm under the division. Okay, integer division by means of two algorithms, restoring and non-restoring. Okay, so your final note, so you take this example, binary decimal number I am giving. Okay, 27 by 11. Okay, so convert this into binary and do the computation for two categories of algorithm, restoring and non-restoring, and post it in the Great Learning. Okay, so that's it about today's topic, and I'll meet you in the next session. Till then, thank you all.